Set is very simple. The only thing that we may need is Minkowski sum. Okay, I mean set, well, you know this, you know this, you know this, right? And then what else? Union, complement, intersection, Cartesian product. Yeah, that's it, right? Then what's the new thing? Minkowski sum. Is that A plus B? Okay, I write M here to say this is Minkowski sum. Is a set. Or the A plus B, that A is in A, B is in B. Something like this, right? And Minkowski sum is useful because later we will have the following. Min F plus G. This guy not differentiable. This guy differentiable. This guy not differentiable. So we have subgradient. This is a set. So we have set plus something. So this is actually Minkowski sum. So that's why we have to do this. And in some situation, we will minimize two non-differentiable things. Then we will have subdifferential 1 plus subdifferential 2. Then these are Minkowski sum. Then what are the geometry of Minkowski sum? Well, Minkowski sum is all the A in A plus all the B in B, right? Then we can just do the following. For example, A is a line 0, 1. B is a line 1, 0. Then A is red. Okay, B is green. Nobody color blind us, right? Then what is A plus B? This line. So this line plus this line give you a box. And then there are some other funny things. For example, a box plus a circle. It will be, okay, this is very difficult to draw, but yeah, you understand what I mean, right? Because it's all the A plus all the B. You can do it by the definition, and then you think about it, and then this is the idea, and then you can have triangle plus okay, these are Minkowski sum, okay? It will be what? Something like this, okay? And then of course, if you have more complicated things, for example, a moon plus a house plus a man, okay, I don't know what does it look like, but anyway, you got the idea. So this is important. Then you have differentiation, okay. Only 10 more minutes. I don't think I have enough time to talk about this, but okay, maybe next week. So let me talk about what we will talk about later. That is, finally, we will go to, for example, what is this? How do you find the derivative? That is, okay, using the directional derivative. Okay, matrix X plus a small t. This is the perturbation. That means a small e minus determinant X t. This is the directional derivative at direction E of what? Determinant function at a funny point X, right? This is directional derivative. E will be equal to inner product between the E and something, a linear map. This will be the gradient, so that means this is the thing. That means if I can write it as something like this, then I find this thing. Then using this, you can find any derivative. And even more complicated one, for example, what is this thing? The gram matrix plus delta I, delta is a number, let's say 5. And then determinant, and then log. Yeah, what is this? Find the gradient of this. I can tell you, you cannot find this in matrix purple. That means what? That means you really need to know how to find the gradient. And then of course, suddenly I put a square root here, then suddenly it's very difficult. Yeah, or I put a square root here. How do you solve this kind of thing? You will need to use a lot of composition rule. You can see this as what? I have A function which map X to X transpose X. I have a B function which map X to X plus delta I, in this case 5. I have a C function that is what? Determinant of X. I have a E function is log something. Then this is basically what? A very complicated chain rule of E of C of B of A. And then what? Now, I don't care what is inside. I call it Z. Well, log is so easy, 1 over Z, right? Then you have the thing inside. Then you now remove one layer. You now do this. And then once you finish it, you remove this layer. You do this, and then you remove this layer, and then do this, then you finish. This is the thing we need to know. What happens if I suddenly put a 4 here? Okay, I am very sure matrix code book have know this. Or what happens if I have a here? Yeah. And then I have some research paper that I have a matrix Y transpose, and I have a diagonal matrix in the middle, and I have a vector V, and I want to find this V. And this is inverse. Okay, how do you find it? You can just this kind of thing, repeated many times. And what happens if I have a determinant here? Or what happens if I have a log here? Yeah, so this is why it's useful. And I almost forgot, oh my gosh, I forgot one very important thing. I also forgot, this is also an important thing. Okay, let's talk about it, then we finish today. So 0 plus delta is fx0, this is one dimension, okay, one dimension, R1, okay, plus f this x0 plus this, right? Right? Then what about multi-dimensional version? Multi-dimensional version, now I write this, okay, it will be, this is Rn to R, okay, this is R to R. It will be something similar, x0 plus delta V, okay, it will be fx0 plus, now this becomes inner product, gradient of fx0, and this is V, right, V, and then plus, this will become Hessian, I write Hess, okay, x0, okay, not enough space, I make it bigger. Hess, which is just this. I write Hess instead of this because some people confuse it with Laplacian from the PDE, but anyway. And then this is the matrix, and then what? V, and then V, something like this, and then divided by 2 factorial. Then what about the third one? Well, in one dimension easy, you have 3 line, and then, right? Well, you can do the same thing here. Then you have some very complicated thing, okay? Differentiate 3 times with PQR, I call it PQR, something like this, and then you have the V, and then V, and then 3 factorial, right? This is the power 3 derivative, but we will never go to this kind of matter, so we don't care. So this is the second order Taylor expansion for multivariable, and this is very useful. Why? So if f is convex, then we have this. Yes, so let me say this. This is equal, but if f is convex, we have this. And if we have this, then we can, what? We don't care this anymore. So we always have something. Okay, I made a mistake. Actually, it's this. But anyway, so we will talk about it when we talk about convex function. So when we have this, this is useful for the argument. I talked about it yesterday a little bit, right? So whenever we minimize the function, we actually don't see the black thing. We always just see the red thing. We are here, we build a red curve, and then we minimize up to here, and then go to here, and then at this point, we build another red thing, and then we go to here. So this is how we actually do gradient descent. Every time when we are doing gradient descent, we actually do not see the black thing. We only see the red thing. Here's the argument. If we know everything about the black thing, that means we already know the minimizer of f. Why can't we just jump to here? The reason why we cannot jump to here is because we never see the black thing. Drawing this line is wrong. Drawing this line is just for human to explain. In reality, what we have is we have a point somewhere like this. And then what does it look like? We don't know. We don't know. We don't know. We just have this. And in practice, we actually have this. The function value, that means the y-axis here, the slope at this point, and the curvature of this point. So actually we only know x, we only know fx, we only know fx, the gradient, that means the slope, and also we know the Hessian. So actually we only have this, and everything here is question mark. So therefore, what are we doing? Actually we are building a red thing, or now we go to this point. So now we have go here, and these are empty, we don't know. So actually, for those books, drawing this is wrong. Okay, if we know this curve, we already know the solution. Why do we even need to do gradient descent? We actually do not know the curve. We only see this kind of point jumping in mid-air. The idea is to build some red thing so we can jump. So therefore, understanding the red thing is very important. And this red thing is exactly second order Taylor expansion. That's why calculus. Okay, so let me recap. What's the thing today? So the thing today is linear algebra. Again, review. I don't talk about detail. For example, what is eigenvalue? Okay, when does eigenvalue exist? Symmetric matrix always have real eigenvalue. Okay, go back to the book. I don't talk about the detail. Topology is open, closed, compact, interior, boundary, open bore. Okay, calculus is calculus. Okay, set is Minkowski sum. This one next week. Okay, so that's all. Good lunch.